Okay, so now we are back to the stationary distribution. Here we'll now introduce what is called the limiting distribution. Now, probability distribution pi is called the limiting distribution of a Markov chain. If for all ij in S, if you look at the Pijn, the n-step transition from y to j, this probability converges to pi j as n goes to infinity. In other words, this limit has no dependence on I, it only depends on j. So in other words, pi is the limiting distribution of Markov chain Xn if and only if under each pi, under when the Markov chain starts on a particular state I, okay, Xn converges in distribution to a random variable x, which follows the distribution pi as n goes to infinity. Okay, so under each pi, Xn as n goes to infinity converges in distribution to a random variable x following the distribution pi. Clearly, limiting distribution, if exists, is unique. It may not exist, but obviously it is unique because each of these limits, it's completely determined by the transition matrix. So once you compute the n-step transition matrix and then take the limits, that should give you this point. So therefore, this has to, if at all it exists, it has to be unique because the limit is unique. Each of these limits are unique. But the point is, it may not exist at all. Now here is another result which says that if the limiting distribution exists, then it is also a stationary distribution. Why is that so? Let's try to prove this. Note that for each j in S, ij is just this limit of Pij n plus 1. Instead of n, I have n plus 1 as n goes to infinity. Now I wrote it as Pij n plus 1, therefore I would write it. Remember, p power n plus 1 is p power n times p. Using that, or you can say using Chapman-Kolmogorov, whatever. What we get is that this is the sum of Pikn times Pkj, sum over k running over S. So this quantity here is equal to this sum. Now we take the limit as n goes to infinity. Now if we could take the limit inside the sum, then it would be nice, right? So if we could do that, if we interchange the sum and the limit, then of course this limit will go inside this sum. And then of course this limit we know as n goes to infinity, if the limiting distribution exists, it has to be pi k. So this would be pi k times pkj, which will establish that pi is indeed a stationary distribution. But this would be true provided if we could interchange the limit and sum here, provided this step can be justified. Unfortunately, this step cannot be justified with the help of dominated convergence theorem, because for every fixed j, if you look at pkj and run k over s, so this is basically looking at the jth column of the transition matrix that does not follow a probability distribution. The jth column of the matrix actually formed a probability distribution, then using dominated convergence theorem, one could actually interchange the sum and the limit. So therefore, we cannot, so this may not be a probability distribution. That's what I am saying. It can be sometimes, but not necessarily this is a probability distribution. So therefore, this interchange in general is not possible. But the key point here is that there is one case where this interchange is possible, namely when the state space S is finite. So therefore, by using this argument that I have given here, when S is finite, we are done. If S is finite, then this interchange is allowed, and therefore we are done. This shows that pi is indeed a stationary distribution. This equation here shows that pi is indeed a stationary distribution. If not, then what we would do, it's a countable state space. We'll just approximate the countable state space by a finite state space and try to carry it through the argument. That's the idea. Okay? So if S is finite, then we are done. So therefore, assume S is countable. And since S is countable, in this case, it's easier to give it a name. So let's just call it, this is 0. This is a set of all non-negative integers. It doesn't matter. You can always rename the states but here we are just renaming it this way so that it's easier to write down the proof. Okay? Just for the ease of writing down, we are just assuming S to be the set of all non-negative integers, which is obviously a countably infinite set. So then in that countably infinite S, now we have to give the proofs. As I said, we'll approximate it by finite state space. So what we would do is remember that pi j is the limit. So this is what we have obtained already. Pi j is the limit of these guys, right? So pi j is the limit of these guys. Now what I would do is, instead of taking the sum all the way from k to infinity, I'll take the sum from k to m. K equal to 0 to infinity. I'll take it from k equal to 0 to m. Okay. By the way, this is true for all state j. Okay. And then obviously this will give us an inequality because we are dropping a bunch of non-negative terms. Okay. Now, once you have that this is a finite thing, of course this limit and sum can be interchanged. The limit of a sum is sum of the limit if you have finitely many quantities. So therefore, this limit can go inside. And of course, this limit will give me pi k. So therefore, this will give me pi k pkj. Of course, this is true for all m in n. Therefore, taking limit as n goes to infinity, we'll get that for all j in S, pi j is actually bigger than or equal to sum of pi k pkj. However, we have to prove equality. Remember, we have only proved the inequality. We have to prove that pi j is equal to this guy to show that pi is indeed a stationary distribution. We have to show that for all j in S, pi j is equal to this. We have shown it is bigger than equal to this. Now we have to see how to show the equality.